All right, so we're diving into this Allegro paper today, really digging into this whole text-to-video thing. Looks like the team at Rhymes AI has been busy.
Yeah, they've been pushing the boundaries here for sure.
Lots to unpack, I think. Where do you want to start? What jumped out at you?
Well, right off the bat, their commitment to data quality. That's huge. They didn't just grab any old data set.
Right, right. I mean, you need good ingredients for a good meal, right? So what do they do?
They built this massive data set, over 106 million images and 48 million videos. And it's all meticulously annotated.
Wow. That's a lot of data.
It is, and they were very intentional about it. They used this multi-step filtering process to make sure it was all top-notch, weeding out any low-quality stuff.
Makes sense. Garbage in, garbage out, as they say. But they also did something interesting with aesthetics, right?
Yeah, they incorporated the elon aesthetics predictor. Basically, they're training an AI with a sense of style, you know?
So like an AI that's not just spitting out technically correct videos, but ones that are actually visually appealing?
Exactly. They think of the whole package, and that really comes through in the results, too. It's pretty impressive.
So how does this tag-to-text thing work?
Well, they needed a way to generate captions for all this data, right? And doing it manually would be insanely time-consuming.
Yeah, no kidding.
So they leverage tag-to-text. It uses pre-trained vision language models to automatically generate captions from image tags.
So it's like a shortcut.
Yeah, you could say that. It streamlines the whole annotation process so they could scale up their efforts without compromising quality.
Clever. So now they have all this beautiful data ready to go. What's next? How do they train a model with something this huge?
That's where their video VAE comes in, Video Variational Autoencoder. It's like a super efficient compression engine for video data.
Okay, break that down for me. What does it actually do?
Imagine you have a huge video file, millions of pixels. The video VAE compresses it down into a more manageable form. But here's the key. It doesn't just squish it down indiscriminately.
Right. It needs to preserve the important stuff.
Exactly. Their video VAE is designed to keep all those fine details, all the nuances of motion, all while making the data smaller.
So it's like a smart zip file.
A really smart one, yeah. And it plays a huge role in making the whole training process feasible.
What makes their video VAE stand out? I mean, there are other VAEs out there, right?
There are, but theirs is specifically designed to capture both the spatial details within each frame and the temporal flow across frames. It's not just about individual snapshots, it's about the whole movie.
I'm picking up on a theme here. Lots of focus on preserving the richness and complexity of video, not just treating it like a bunch of static images strung together.
Exactly. That's one of the things that sets Allegro apart, I think. That attention to detail to capturing what makes video unique.
Could you dig into the technicals a bit more? How does their video VAE actually achieve that?
Well, a big part of it is incorporating temporal modeling layers into the encoder and decoder architecture. Specifically, they use 3D convolutional neural networks.
3D CNNs. Okay, now we're getting into the weeds a bit.
It's not as complicated as it sounds. Think about it this way. A regular 2D CNN looks at a single frame and analyzes the spatial features. But with a 3D CNN, it can analyze those features across multiple frames simultaneously. It can see the motion.
So it's like giving the AI depth perception.
That's a good way to put it. And it allows the video VAE to really understand the dynamics of the video.
I'm curious about the training process for this video VAE. Did they do anything special there?
They were quite clever about it. They used both images and videos for training.
Interesting. Why both?
Well, they had this huge amount of image data available, so they wanted to leverage that. But they also needed the video VAE to learn those temporal dynamics specific to video, so they used a mix of both.
Smart. Get the best of both worlds. Anything else noteworthy about the training?
They used a combination of L1 loss and LPIPS loss.
LPIPS loss. I'm not familiar with that one.
It stands for Learned Perceptual Image Patch Similarity. It's a perceptual loss that's more attuned to how humans perceive visual similarity. It goes beyond just comparing pixels. It's about capturing the essence of the image.
Sounds like they're really trying to teach the AI good taste here.
Yeah, you could say that. They wanted to understand what makes a video look and feel right, not just replicate pixels.
But all this must be incredibly computationally intensive.
Sure.
How do they deal with that?
They did a lot of optimization. One really interesting trick was using tiling during both encoding and decoding. Essentially, they divided the video into smaller chunks, like puzzle pieces.
Okay, I'm following.
They encode and decode each tile separately, which reduces the memory requirements, and then they stitch them back together seamlessly.
So like parallel processing for video.
Exactly. It's a brilliant way to handle those high-resolution, long-duration videos without needing a supercomputer.
It sounds like they went to great lengths to optimize this video VAE. What kind of results did they see?
They compared it to existing open-source models using metrics like PSNR and SSIM.
Those are the standard benchmarks, right?
Yep. And their video VAE outperformed the alternatives, showing that it could achieve high-quality reconstructions with minimal loss of information. It's a really solid foundation for the whole system.
It sounds like it. All right, so we've covered the data and this impressive video VAE, but now I really want to hear about the heart of the operation. The video diffusion transformer, or video DT.
That's where the real magic happens, right? Turning text into video.
Exactly. But before we jump into that, can you give me a crash course on diffusion models in general? How do they work, especially in this context?
Imagine taking a clear picture and slowly adding noise to it until it's just random pixels. A diffusion model learns to reverse that process. It starts with pure noise and gradually removes it, guided by the information it's learned from the training data.
So in this case, it's guided by the text prompt and those compressed video representations from the video VAE.
Precisely. It's like starting with a blank canvas and slowly revealing a picture, guided by those two sources of information.
Okay, that makes sense. But where do transformers fit into all of this? I know they're a big deal in AI, but how do they help generate video?
Transformers are amazing at understanding relationships between different elements in a sequence. In the video DIT, they're the ones that really figure out how everything fits together, how different parts of the video relate to each other, and how the video relates to the text prompt.
So they're like the brains of the operation, making sure everything makes sense and follows the instructions.
That's a great way to put it. And their implementation of the transformer architecture is really innovative. They use full 3D attention.
3D attention? I'm intrigued. What's so special about that?
Earlier models often used 2D spatial attention and 1D temporal attention separately. So it's like they were analyzing space and time as separate things.
And that's not how we experience video, right? It's all integrated.
Exactly. With 3D attention, the model can analyze both space and time together. It can understand the flow of movement in a much more natural way.
It's like watching a dance instead of looking at a series of still photos.
Perfect analogy. And that's one of the key innovations that allows Allegro to generate such realistic and fluid videos.
I'm already impressed, and it sounds like we're just getting started. I'm eager to learn more about the specifics of the video DDT architecture, but I feel like we might be running out of time for this part.
Yeah, maybe we should save that for the next part. We can dive into the DIT blocks and all the cool stuff they do.
Sounds like a plan.
Yeah.
Looking forward to it.
All right, so we left off talking about how they train this intricate video DDT. And it's a multi-stage journey, a bit of a winding road. It all starts with text-to-image pre-training.
That seems kind of counterintuitive, doesn't it? I mean, the goal is video, right? Why start with still images?
Think of it like this. It's all about laying a solid foundation. You got to learn the alphabet before you can write a novel, right? This stage helps the model grasp the connection between words and images.
So it's like priming the pump, getting the model familiar with the basic building blocks before moving on to the complex stuff.
Exactly. And they didn't just use any old text-to-image model either. They took a pre-trained model from OpenAI, swapped out the text encoder with T5, and replaced the VAE with their custom video VAE.
That's interesting. So they're using components that are already aligned with their final architecture.
Right. Makes the transition to video generation a lot smoother. And they cleverly incorporated static frames from videos in this text-to-image training phase. So it's like showing the model snapshots from a movie before they watch the whole thing.
I see. So they're already exposing the model to both static and dynamic visual elements right from the start, like planting those seeds of understanding.
Precisely. And then comes the really exciting part, text-to-video pre-training. This is where they used a progressive strategy, gradually ramping up the complexity.
I'm guessing this is where the whole start small and scale up approach comes in. Pretty standard in deep learning, right?
Yeah, exactly. They started with a more manageable task, 40 frames at a resolution of 368 by 640. Then they upped the ante, 40 frames at a higher resolution, 720 by 1280. And finally, they pushed it even further, increasing the frame count to 88 while maintaining that higher resolution.
So like training wheels, then a small bike, and then finally the big leagues. But I bet even with that gradual progression, they still hit some snags along the way. Training a model like this can't be easy.
Oh, they definitely encountered challenges. For example, at lower resolutions, they noticed some jitter in the motion of finer details,
Jitter. What do you mean by that?
like a slight flickering or instability in the movement. They attributed it to limitations in the video VAE's ability to model those details effectively at such low resolutions.
So it shows how everything is interconnected, right? Limitations in one area can have a ripple effect. Like a chain, one weak link can bring down the whole thing.
Precisely. And even at higher resolutions, when they were working with shorter video durations, they saw some distortions, unnatural motion.
Interesting. Why do you think that was?
It seems like the model needs a certain number of frames to really grasp and represent those more intricate movements accurately. You can't just create individual frames. It's got to flow smoothly over time.
Like the difference between a flip book and an animated movie, right?
Yeah, great analogy. Each frame contributes to that overall coherence, that fluidity. Too few frames and the model struggles to capture the nuances of motion.
So they tackled the image-to-text foundation and progressively trained the video DIT to handle longer, higher-resolution videos. What's the final stage?
Text-to-video fine-tuning. This is where they refine everything. They use a smaller set of high-quality videos and diverse captions. Think of it like polishing a diamond, taking a model that's already good and making it shine.
Taking it from apprentice to master craftsman up.
Exactly. This multi-stage training approach is how they achieve such impressive results with Allegro.
But all of this must require massive computing power. How did they manage?
They were very strategic about it. They implemented some really smart infrastructure optimizations. A key one was decoupled inference for the VAE.
Decoupled inference. Okay, I need you to break that down for me.
Encoding and decoding video data with the VAE is computationally heavy. So they cleverly offloaded those tasks to separate less powerful GPUs, freed up the high-performance GPUs to focus on training the video DT.
It's like having a specialized team. You have the heavy hitters handling the core tasks and a support team taking care of the rest.
Exactly. They optimized resource allocation and sped things up significantly, but they didn't stop there. They also used things like JIT compilation and batching inference for the VAE to really squeeze out every bit of performance.
They're leaving no stone unturned. It's clear they put a lot of thought into not just the model itself, but also how to make the training process as efficient as possible.
Absolutely. They really went the extra mile.
Any other optimizations worth mentioning?
Yes, they also focused on optimizing the attention mechanisms within the video DIT. Attention is crucial for understanding relationships, but it can be a computational bottleneck.
Especially with video data, right?
Yeah.
Those sequences can get pretty long.
Exactly. So they use flash attention too. A very efficient implementation of attention reduces both memory and computation.
So they found a smarter way for the model to pay attention, so to speak, without getting bogged down.
Right. And they use flash attention too specifically for self-attention. For cross-attention, they used X-Former's memory-efficient attention.
So they were very deliberate about choosing the right tool for the job, always with an eye on efficiency.
Absolutely. One final optimization worth highlighting is context parallelism. Basically, they distributed the processing of those long sequences across multiple GPUs.
Makes sense. Divide and conquer.
Right. Exactly. It allowed them to handle the enormous context length required for their model, nearly 80,000. That would have been impossible on a single GPU.
It's impressive how they've optimized every step of the way. They weren't just satisfied with a great model. They wanted to make sure it could be trained effectively and efficiently.
It's a great example of balancing innovation with practicality.
I'm eager to hear how all this translates into actual performance. Let's move on to the evaluation and see how Allegro stacks up against the competition.
All right, time to see how Allegro actually performs. And they didn't just focus on the numbers.
Right, video's not just about technical specs, is it? It's about the experience.
Exactly. They wanted to understand how people felt about the videos too.
So how did they go about evaluating it? Did they just, watch a bunch of videos and say, yep, looks good?
Well, they started with VBench.
VBench?
It's a benchmark designed specifically for video generation models. Assesses stuff like video quality, how well it aligns with the text, that sort of thing.
So it's like a standardized test, see how it compares to other models.
Exactly. And Allegro aced it. Outperformed all the other open source models on every single dimension measured by VBench.
Wow. That's impressive.
Yeah, it even went head-to-head with some commercial models like Gen 3, Kling, Hailu. Held its own, for sure.
That's really impressive. But like you said, numbers only tell part of the story. What about the human element?
They did a user study, too. Had participants rate the videos on things like how well they matched the text prompt, visual appeal, how natural the motion felt, overall quality, the whole 9 yards.
So a more holistic view.
Exactly. And the user study basically confirmed what VBench showed. Allegro consistently outperformed open source models, even beat most commercial models in several areas.
Like what? What stood out?
Video text relevance was a big one. The generated videos really captured the meaning of the prompts.
It makes sense. All that work on the text encoder and cross-attention really paid off.
Yeah, for sure. It shows they're not just generating pretty videos, they're generating meaningful videos.
Yeah.
Videos that align with the user's intent.
So it sounds like Allegro's a pretty solid all-arounder. Were there any areas where it struggled?
There was one challenge they highlighted: handling large-scale motions. Like, if the video involves big camera movements or lots of action, Allegro's performance wasn't quite as strong as some other models, like Hailu and Kling.
So there's still room for improvement.
Definitely. But they're already brainstorming ideas, like training on more data with those kinds of movements, refining their filtering process even further, maybe even scaling up the model size. They're not resting on their laurels.
That's great to hear. Always pushing the boundaries. They also did some ablation studies, right, to see how each component contributed.
Yeah, they looked at the impact of the text encoder and the multi-stage training strategy.
So like taking the model apart and seeing how each piece works.
Exactly. And they found some interesting things. For example, comparing the T5 text encoder to the original MT5 showed that using an encoder that's optimized for the language of the data makes a big difference.
I guess it makes sense, right? The right tool for the job.
The videos generated using T5 had better visual details, and they were much more aligned with the text prompts. It's like choosing the right paintbrush. It can have a huge impact on the final painting.
Love that analogy. And what about the multi-stage training? What do they learn there?
It basically showed how the model's abilities evolved over time. In those early stages with the lower resolution and fewer frames, it was really focusing on the basics, learning about motion, how to make things move smoothly from frame to frame.
Laying the groundwork.
Yeah, and then as they ramped up the resolution and frame count, the model got better and better at generating complex movements. And then that final fine-tuning stage with the high-quality data and diverse captions, that was like the finishing touch. Really polished it up.
It's amazing to see how all these pieces come together. They really thought this through.
Absolutely. This deep dive into Allegro has been fascinating. It really shows the potential of AI for video generation. And it makes you wonder, what's next?
What is next? It's mind-blowing, really. Creating high-quality video could become as easy as writing a story.
Imagine the possibilities. Anyone could bring their ideas to life, no matter their technical skills.
It would be a revolution for storytelling and communication. It's exciting to think about.
Allegro is a testament to human ingenuity, to what we can achieve with AI. It's a collaboration, our creativity combined with the power of AI.
This has been an incredible conversation. Thanks for walking me through all of this. I'm definitely inspired.
My pleasure. It's a really exciting field, and I'm eager to see what breakthroughs come next.
And to our listener, we hope this deep dive has sparked your imagination as well. Maybe even inspired you to explore the world of AI video generation yourself. The future of video is here, and it's full of possibilities. What story will you tell?